Welcome to Ulurover, the official rover team of Uluda University. My name is Sahajishana and I am captain of Ulurover. We founded this team in 2023 where we developed our first Hajar. Then in 2024, we got a chance to go to ERC, Anatolia Rover Challenge, with our first generation of rover, where we secured 8th position. Now in 2024, we are excited to come to ERC with a completely new design, a completely new generation of rover, Ulurover 2.0. We are a dedicated team of 20 students coming from all different departments, including engineering, science, even business-related studies. The reason to join ERC is to get experience, gain knowledge, and to show the world our engineering solutions.
Rover is organized into 5 main departments: electronics, mechanics, science, software, and organization. Each team is led by a dedicated coordinator who ensures smooth communication and collaboration within the team.
We hold weekly general meetings and regular department sessions to keep everyone aligned. Our team uses Asana for project planning and task tracking, making sure deadlines are met, goals are clear, and responsibilities are shared efficiently. With Asana, we map out each phase of the project from research and prototyping to manufacturing, testing, and presentation. We're proud to introduce our official website where you can follow our progress and learn more about the team. Our website isn't just a display, it's an experience. Here we showcase our high-performance rover designs, cutting-edge components like the triple chassis, and a clear look into our journey through advanced drone systems and robotics engineering. This is more than a website. It's a digital reflection of our team's ambition, creativity, and technical power. We're proud of what we've built and even more excited for what's ahead.
Our rover features a 6-wheel drive rocker buggy suspension system, crafted entirely from aluminum. This gives the rover remarkable stability and mobility, allowing it to navigate over rough terrain and obstacles, much like those you would encounter on Mars. We have also designed a 6-axis robotic arm capable of operating both a precision gripper and a drill. This allows the rover to interact with its environment, collect soil samples, and perform scientific tasks autonomously. Whether it is grasping objects or drilling into the surface to extract geological data, our design can do them both.
Our movement system is 97 by 105 by 38 centimeters in length and has a weight of around 35 kilograms.
The robotic arm we designed for ERC consists of worm gears. It has 6 axes for more flexible movement. We use steel when making shot and gears to increase the durability and reduce the friction. The other materials we use in robotic arm, aluminum and filament, as it reduces the weight. There are gripper and drill mechanism top of the robotic arm. We use simple gripper mechanism to take sample on the surface on the Mars, and we use archement mechanism to drill mechanism.
The arm, which is 130 centimeters long and extend with a radius of 100 centimeters, the arm weight is around 25 kilograms. The biggest advantage of using worm gear is that the system does not slip back. The disadvantage is that it is difficult to manufacture.
Hello, I'm electronic captain of the Ulurover team, and today I'm going to introduce you our electronic system part by part. So let's get started with our block schematics. This is the block diagram of Ulurover. The central controller is the STM32F401 microcontroller. It collects data from sensors and sends commands to other units. We use a BME sensor for temperature, humidity, and pressure, and MPU for orientation, and a load cell for weight measurement. Communication is handled through I2C and UART protocols. For advanced tasks like image processing and navigation, we use both a Raspberry Pi 5 and a Jetson Nano. Jetson uses as a stereo camera for depth perception. Motor control is handled by STM. It is chosen for its advanced motor control timers. We use custom designed PCBs with L293D drivers for DC motors, and 4 DIV268 and drivers for stepper motors. Power is supplied by 6S LiPo batteries. For safety, power goes through a fuse and emergency stop system before reaching the power distribution board. We couldn't find any power distribution board that meets our requirements, so as a team, we designed one.
Hello, I am designer of this power distribution board, and I'm gonna introduce it to you. Our rover needs a lot of power, so we designed a special power distribution board. It gives different voltage for different parts. There are 2 5V outputs and 1 3.3V output, and 2 battery voltage outputs. The 5V outputs for Raspberry Pi and Jetson Nano, they need a lot of current. We use an XL4015 voltage regulator. It gives up to 5A current, and it does not last too much energy. It is good for our small computers. We use terminal blocks for power, and XT60 for the main input. We also use a 25 amp fuse for safety. It's got the power if something goes wrong.
Hello, in this part I am going to mention Rover's safety systems.
We use an emergency stop button that holds all the power less than 1 second. Also, to ensure safety, power goes through a fuse before reaching power distribution board. Our visual indication system consists of 3 power LEDs that shows rover's condition.
Our drone is built on a carbon fiber X-frame. It uses 4 2212 920 kV brushless DC motors and 20 amp electronic speed controllers for precise control. At its core, there is the Pixar flight controller with autopilot firmware. It supports both manual and autonomous flying via mission planner. Powered by a 3S Super battery, it flies for 20 minutes. A VC transmitter and telemetry module ensure stable communication and real-time data transfer.
For autonomous navigation, we will be going this year with a hybrid approach. We will be using ROS 2 with our custom scripts. Autonomous navigation is divided into 3 parts: perception, mapping and localization, and motion control. For perception, we will be using Z2 camera as a sensor. The Z2 camera will give its sensor readings as point cloud information to the ORB SLAM 3, in which we will be doing the mapping and localization. The ORB SLAM algorithm will provide keyframes, camera trajectory, and map points, which is used by the nav2 stack in ROS 2 to plan safe and efficient paths. For motion control, the rover uses a differential drive system controlled through ROS 2 with a custom hardware interface. This converts high-level velocity commands into motor commands.
Image classification is divided into 3 different stages: the capturing, segmentation, and classification. For segmentation, we use the UNet/CNN algorithm. For classification, we use an efficient innate B2 algorithm. And for capturing, we use the onboard webcams on the rover. In a test of 30 random-generated images, we were able to get an accuracy of 0.8.
Between ground station and rover, we used the light beam 120 as main communication system, which supports communication up to 5 kilometers at 5.8 GHz band. Additionally, we used a telemetry radio as a backup solution in case the main communication system fails. We enabled teleoperation from ground base using both keyboard and joystick control.
The goal of the Ulurover science team is to provide a solid foundational scientific hypothesis to serve as the basis for the rover's activities and design. And this year's new and improved science payload consists of a Raspberry Pi 5 controlled automated mini lab to conduct both sampling and testing on board the rover to minimize the effects of environmental contamination.
The physical sampling system consists of a 3D printed PLA drilling mechanism capable of reaching depths of up to 30 centimeters. The onboard mini-lab processes up to 3 soil samples and 1 rock sample, keeping them protected from the environment. Soil samples are split for separate tests. Some are mixed with water for analysis, while others go through gas testing. A rotating drum removes samples past a camera for imaging, and a weight sensor tracks the soil changes. All liquids are handled by peristaltic pumps. Our hypothesis centers on the past or present existence of sulfur-reducing microorganisms on Mars. To investigate, we assess habitability using data from our onboard weather station, measuring atmospheric gases like hydrogen and methane, UV levels, and temperature. Each soil sample is tested for pH, sulfate, and iron ions, which are key to microbial metabolism. One of our core experiments uses hydrogen peroxide to react with soil compounds, producing gases like carbon dioxide if life-related organic molecules are present. This gas evolution is measured with onboard sensors and serves as a preliminary life detection test. Complementing this, we've developed an in-house rock identification model using PyTorch. Trained on a curated dataset of region-specific rock types, it runs through a Shiny-based interface and helps us identify rocks that could reveal more about the site's geologic and potentially biological history.